I speak again?
Yeah, the chat says yes.
Now it should work? Fine. Okay.
I restarted the recording, so maybe you just say...
You restart the recording. Okay, good. Yes. So, we will explain the real-time iteration on an extremely simple setting and then compare it to the ILQR method that is also used a lot in the dynamic programming or in the reinforcement learning community. So, the setting is, as I said, without inequalities, and we have just a system dynamics, some constraints here, and these are the source of nonlinearity of our problem. So this is the problem I want to look at. And I say before, C and E are quadratic functions, and they are convex. For example, you could think of something like S transpose Q S plus A transpose R A, right? Typical quadratic cost. I will use this notation here in order to not get lost in matrix notation, but please keep in mind one thing that we know already, and that is if we would have a system that is linear, if that system was a linear system, actually affine is enough, right? Something, if f of S and A is equal to something like A, I, and okay, it could be with an index. Let me add an index here. AI, SI plus BI, AI plus CI. CI is a vector, A and B are matrices. That could be time varying. Yeah, and if CI is convex quadratic, right? But it could be time varying as well. That's important here, contrary to this notation. But if we have that, then what happens? Then we know that the optimal solution is a linear feedback law on S0, right? So then we know, well, that's a very basic thing from linear algebra, we can derive it, but we would then A0 star, yeah, as a function of S0 bar, yeah? This is like the optimal feedback law, is something that we call K0 times S0 bar plus some vector, I call it V0. And we can compute that by a by a backward Riccati sweep. Backward Riccati. And you remember there are these slides with the inhomogeneous system and inhomogeneous cost. That's what basically makes this vector appear. Yeah? But basically, it's an affine function of the state. This is a beautiful result, isn't it? Right? So now, and this whole result works by generating not only the feedback law for the time step 0, but an implicit thing that's, so to say, coming also into play is that we also get a kind of approximate feedback for all other states on the horizon. It's not approximate for the linear quadratic case, it would be the exact. Yeah? So we would also get like AI star equals KI SI star plus VI. So we get also other feedback laws which would actually, for MPC we are only interested in this linear feedback law. That's the only thing we need in MPC. So we could stop here, right? If we have a linear quadratic problem with linear system model, even if it was time varying and so on, afterwards, after we have solved it, we could just store the K and the V and then we are done, right? But you could also say, okay, I'm interested in the trajectory that is optimal for this quadratic problem, and then I could actually forward simulate my system, this linear system, of course, and I could generate my controls by this linear law, and then I can actually recover my whole solution to the QP. Yeah? Okay, first question. This is like important. Thank you. Perfect. Yeah, I asked actually Joschka to ask whatever question comes to his mind. Yeah, please ask it. Yes, you can even come to the camera or yeah.
I was just to be clear on the notation, maybe right. So this star here, what does it indicate for the state? I mean, this is the optimal control law. So this is already part of the optimal trajectory then, or what does it indicate exactly?
Okay, yep. So thank you for the question. I was a bit fast and maybe too sloppy here. So if we have a time-varying but linear system, then we could solve this whole problem. And we could get the whole solution to the problem, which I denote, and maybe I still devote some space to it on the right. So this is like the QP. I call it for QP, right? For the QP. I call it a QP. It's without inequality, but it's still for a QP. So for the QP solution, I would call it A star 0 up to A n minus 1 star, and S 0 star up to S n star. So that is just the solution to the QP. If you would now replace this with a time-varying Fi that's of this form, and this convex quadratic time-varying with that form, and Ei would be also quadratic. Okay, and the algorithm to get it, get via Riccati, as we said before. And as follows, we just set S 0 star to S0 bar, right? So that's a constraint. That's so trivial. We just set it to that value. But then we have this loop. So for I from 0 to n minus 1, we do the following. We actually first compute our control, Ai star, and we have these pre-computed matrices, which basically take our optimal state at that time point and send it through an affine function, which we have computed from the Riccati iteration. And that gives us this feedback law. And that tells us what would be the optimal A for that state. And then the state is propagated via the system dynamics. That means in this case Ai Si star plus Bi Ai star plus Ci. And this was the original system. Yeah? And so Riccati is a backward sweep. Yeah? Remember, in your computations, we would need a backward sweep that computes all these things, and it has internal memory with these P matrices and so on, but we are not interested in the P matrices at the moment. I'm just interested in the K matrices, which are also generated. So I've hidden the Riccati equation here. It's a long equation, and I don't even remember it exactly now, right? But we could look it up. And then it just generates us all these feedback laws, Ki times S plus Vi. What does it mean? What is such a feedback law? It's here we have the S, here we have the A, and it's an affine function. Yeah? And that's like the beautiful result from, anyway, you could look at this, say it's a quadratic program. That's a linear system of equations. A linear system of equations depends linearly on its parameters, so obviously it must be linear, right? But this is like how it's boiled down to the states. And there's a very elegant way to compute it by the Riccati recursion, which is just a backward pass first, and afterwards this is a forward pass actually. Yeah? I call it forward because you need a forward pass here. And okay. So in that sense, for linear quadratic problems, we know how to solve it. That's beautiful. So now comes SCP or Gauss-Newton actually into play, but there is first a question which I will repeat.
Two questions. One related to the CIs, because you said it would be convex quadratic, and there's some notation maybe. Because we have the CI as the linear, like the affine term in the linear dynamics.
Thank you. Okay, this was stupid. Right. So let's just call this maybe little bi. Is that okay? Yeah. Sorry, this was a very bad notation. Thank you for this question. It was just bad notation. So the Ci is the cost.
And this should be.
And this is just a vector. B is just a vector, and this Ci is now the function S of A, right? And it's convex quadratic. Mm-hmm. Okay, LQG, LQR, let's say. I mean, LQG is with an estimator. Yeah? So LQR solves this problem for n going to infinity, basically. That's what LQR does. Yeah? And LQG is LQR plus a Kalman filter, so to say. And I hope that's already giving the big idea. Okay, so now these are just side remarks, so I put brackets around them, but now we have a way to solve a QP, right? And I made it already time varying. Why did I make it time varying? Because in the SCP subproblem, and maybe I should really use a new problem formulation. I will just put it here because we already know most of it. So what we do in the SCP subproblem, you remember we want to linearize that system. And that's the only thing we do. And by linearizing, we get such a system. Yeah? So we replace basically the system dynamics. And maybe let me just focus on the dynamics. So we replace, so for nonlinear, in SCP, SCP, or Gauss-Newton you could also say, because now we do Gauss-Newton. It's nothing else than Gauss-Newton, because just we keep the convex quadratic terms and then you do the Gauss-Newton method. In this case, SCP boils down to Gauss-Newton. We only linearize F at the current guess. And this guess we had this notation before, but we do basically an upper index J, right? AJ. That could be one way to do it. Maybe these indices are a bit nasty, so maybe why don't we do it like I put a bar on top? That's better. S is basically the trajectory at which I linearize. Yeah? This could be a feasible trajectory. It could also be an unfeasible trajectory, and that's basically the difference between sequential and simultaneous methods. Yeah, so this trajectory does not need to satisfy the system dynamics. But what we can do then afterwards, we just have our constraints, and they are saying Si plus 1 is equal to Fl of Si and Ai semicolon Si bar and Ai bar. This is already my personal preferred shorthand. If you want to exactly see what it is, then we can write it down exactly. Is that maybe helpful to say what I mean by this linearization? So I do it. So basically, maybe get a bit used to there are two special things in my notation, right? One is that I just put this L and I say that's a linearization, first order Taylor series, and I don't put all the symbols. The other thing is, very often in Newton type optimization, you deal with steps in variables. I decided at some point to cancel the step and just say I work directly in the space itself, not in the step space, yeah? Which is just a linear step. But everything, I think, gets cleaner and easier. So the only thing we do in the Newton type method is actually replace the nonlinear constraints by these, and then we have boiled down everything back to a QP, right? So that's the beauty of it. And this FL, let me just say it's SA S bar A bar. Yeah? So this is now for a single time step. It is actually the function F evaluated as S bar and A bar at the point where we are. And then it's the first order Taylor series with respect to the first variable, evaluated at the trajectory, and then multiplied with the S minus S bar. That's now the step here. And here we have dF by dA, evaluated at S bar and A bar. Yeah, I keep this argument because we need to know where we linearize, of course. Yeah? And then you multiply this with A minus A bar. So that's the definition, basically, of this linearization. And please keep in mind what it is. If we have A or also S, it's the same, right? S, and here we have F. Then we would have, let's say here's maybe A bar, here's maybe S bar. And if you plot this function from different sides, it could look like that, maybe like that, right? And our linearization at some point gives us the Taylor series at this point. So that's what the linearization does. It's just approximating our nonlinear system with something linear. And it does so at every time step a different one. That's very crucial for all this. That's why we need the even though the f itself was not having a time index, right? After we linearize, because our trajectory has these linearization points, which are different on the whole trajectory, it is a time-varying quadratic system. Yeah? So let me visualize the optimization variables again, just so that we know. So here we would have S0, and then we would have S1, and so on. And at the very end, it need not be at 0, right? But so this is like all the optimization variables, and every variable, I mean, we are now at some point Si, for example, and here at this point, we get some FL at Si bar and AI bar. So even, of course, this dependence on the first two arguments is linear now, but because I have the dependence of the derivatives, in particular of the gains, everything here depends on my bar. This will be a time-varying system. Every time step will have a different system dynamics. Yeah? So it's not the same system every time step, which in control engineering sometimes people also do. They just say, hey, I'm here, so let's linearize. And then I'm applying LQR directly. That's also possible, but it's a very different setup. So here we really look at the trajectory of the nonlinear system, and our aim is actually to solve the nonlinear problem. And so now SCP would just do this by so what was, full step SCP? SCP does the following. It would just say, let's say all these variables together. X is so to say all the A's, all the S's and all the A's together. Yeah? So everything, right? The whole trajectory. So it would just say xj plus 1 is equal to the arc min of QP. And I think we have now in mind what this QP is. It's a QP with this, the QP2, basically. So we solve that QP, and we get a new iterate for the whole trajectory. There we linearize again. We get the same QP, and so what full step SCP needs? What does it need? It needs linearization first. Linearize. So we need to compute these matrices. That's sometimes very costly. That's why I say it. Second thing is Riccati forward, Riccati backward. So we need this backward sweep. And then we need to do the forward simulation, linear forward simulation. I call it linear because it's based on the linear system that we have obtained from the linearization. And that basically solves the QP. So this whole thing is the QP solution. It's nothing else than a QP solution, but it's exploiting the structure of the QP solution. Yeah. Thank you. There is a question by Joschka now.
Just maybe it's picky, but wouldn't you say it's locally linear forward simulation? Because you use these time-varying matrices? Yeah.
Yes. Joschka said, is it a locally linear forward simulation? Actually, it is not a correct forward simulation. It's absolutely a wrong forward simulation, and it's good that you make this point already, because that's the crucial difference here. Yeah? It's actually a forward simulation of the linear system. Maybe I should call it that way, right?
Yeah, exactly.
That's better. Forward simulation of the linear system. The point is, I just do it because it's part of the QP solution, so to say. I mean, the Riccati backward gives me only the feedback law, but only for the linearized point. It doesn't really help me in solving the whole problem. So if I do full step SCP with many iterations, I need to solve the linear system in each iteration. And solving it means not only the Riccati backward, but also a forward simulation of the linear system. Yeah. So this linear system is just used, so to say, to get the A's and the S's, but they have no meaning as physical. I mean, they have a meaning as an approximation of the physical method, right? And this is the usual as Newton-type convergence, let's say, contraction rate. And the contraction rate of all these methods is linear because we have a slightly wrong Hessian. So because this, there would be, it's not an exact Hessian method, but a Gauss-Newton method. Contraction rate, it's typically fast linear convergence. So after, let's say, 10 iterations, you would probably have solved the full problem, and then you have a beautiful trajectory that is, so to say, saying you're starting at S0 bar. We would have somehow solved perfectly our system. Yeah, and I think it's also fair that I use this could be Sn star. But in between the iterates, they will actually be sometimes looking like that, right? So you might have, if you would plot your simulation routine, it could look like that. Yeah. So it's not having feasible trajectories. And that's because the linear system isn't a perfect predictor of the nonlinear system, right? But it's a pretty good predictor, so this is hugely exaggerated. You never see it like that. It's just to show the point. Yeah? But this is like the solution, and this is the intermediate iterate. Is infeasible. So that's, you could say, unaesthetic, right? You don't like that, maybe. But anyway, that's what we do, and I still recommend to do it. Huh? But so now we have the full step SCP method, and I think we already have explained, so to say, the RTI SCP, but let me just do it now in this simple picture. So you would do the same, so to say, but you would just say x, so you basically say xij plus 1 is equal to the argument that minimizes the QP2 at xj, but with the initial value, and now that's a crucial point, we already take the latest initial value that we call S bar j plus 1. So I always take the, because I want the index to denote the solution or the approximate solution to the current problem. So I basically linearize at the old trajectory, but I solve it with the new xsi bar. And now the interesting thing is, if you look at what it does here, so you see that the A RTI, the feedback law that I get, which is a function of Sj plus 1 bar, that this is given by exactly these matrices. So you have, so you can basically pre-compute a lot of things. That's exactly the point here. Namely, if you would do the RTI SCP, what you would do is you would linearize. You would do a Riccati backward. And then you have the K and the V0. And then you take the, and only at that moment, you don't need to know it before. At that moment that you know now the latest state measurement, you multiply it with K0 and you add V0, and then you have your control law. So that's basically this linear feedback law. And afterwards, you would still do the forward simulation that I explained before. And then you have a full new trajectory guess at which you can linearize again. And so in that sense, you see that these, so the preparation phase is linearization in Riccati. And then the we call it also expansion, because you need first to expand the first, the previous solution. I mean, this forward simulation I call also expansion, yeah? Yeah, so forward simulation, it's expanding your solution to the full space, so to say. So first you expand your old solution, then you linearize at this new iterate, then you do a Riccati, and then in the feedback phase, you just apply this thing. So this is, so to say, and then afterwards I do the next expansion. So in that sense, I have now everything that I can do without knowledge of S0 or Sj plus 1, as we call it here. You do it already, and this is the preparation phase, and then there is a feedback step, which is, in this context, just a matrix multiplication. And by the way, it might be that this preparation phase takes very long. So it might be that you need a lot of time for that. So we could even do something that we call multi-level iterations. You could apply this feedback law 100 times while you do the next preparation. Yeah? So you could just say, I give feedback already, and that might usually not do much. Because, but if there is a disturbance coming in between, you could directly react to it, even though you are still computing. So in that sense, it could be an advantage to keep that feedback law active inside a lower level algorithm. So that's the full step SCP. Now we have the RTI SCP. And let me see if we still have time to do the ILQR. What does ILQR now do typically, right? Maybe the first thing is ILQR is in this context. It would be typically mostly thought of as an offline method, so you typically do more Newton iterations. Huh? You could also think of a real-time variant, and maybe we define that afterwards. Let's maybe first do the full ILQR. So let's say it's sequential approach, in the sense that it will only have feasible iterates, like we defined it on the Wednesday lectures. So, but it generates its trajectories in a slightly smarter way. So let me say what maybe I should also explain, but that's maybe too much. I explain briefly what single shooting would do. Yeah, single shooting on this problem, it would linearize, it would do the QP solution. And after it has found the QP solution, it would just take the control trajectory and simulate the nonlinear system with that. And then it could linearize at this new guess. So that would be you could just take the full step SCP and make a little modification. Sometimes people call it feasibility projection. Yeah? So you just after you have your iterate in the full space, X contains of trajectories and states, you somehow say, for some reason, I override my states that I got from the QP solver, and I override them with a simulated approach. Yeah? So that would be single shooting with sparsity exploitation. That's also possible here. But this talk isn't about single shooting with sparsity exploitation, right? This talk is about IQR, and IQR is very similar to that, but slightly different and better to understand when we look at this forward sweep. Yeah? And the idea in the full step ILQR iteration, so to say, is that we just do the forward sweep already differently. So we don't solve a QP actually. Yeah? So get basically this new iterate that we call Sj plus 1, 0, Sj plus 1, 1, and so on. And also the controls, A0, J plus 1. So all these controls, right? You get them after you have done the Riccati recursion like we do anyway. So you so you do linearize, you do Riccati. But then here this forward simulation, this last step, where Joschka rightly directly said, no, why do you simulate a linear system? You know it's nonlinear, right? Why should we do that, right? So we do this differently now, and we do just a forward sweep with the same controller where we just say AI star, call it J plus 1, right, is equal to KI SI J plus 1 plus VI. And of course these matrices are different in each iteration, but I don't want to give them another index also, right? So and then here we have the forward sweep for the states. And that's now the crucial difference. Here we take the nonlinear system, right? So we take S I J plus 1 and I J plus 1. And I forgot to say the initial condition, of course, should be, let's put it at the bottom, S starting at, where would we start? We set S0 J plus 1, 2. Yeah? No, first you don't want to answer, right? So I first answered. We set this S0 to the initial point, which was, S0 bar. So the initial value that we have. Or depending on if you have a sequence of problems, of course, it could be the most current state. Okay, so this is the only difference. So the forward propagation is with the nonlinear feedback. And now if you want to look at it, what it does, it generates intermediate iterates which are feasible, right? So that's nice about it, because it's directly, so it's not having this thing, right? It has feasible iterates all the time, like single shooting, by the way. And it's just a slightly different way to get it. So in single shooting, so to say, you first do the forward sweep of the linear system to get all controls, and then you override all states by nonlinear simulation. So you basically, and in ILQR, you directly generate the controls and the states together by a forward sweep of the nonlinear system, but with a linear feedback law. And then I have slightly, I think this is definitely a bit better than single shooting, because you already have a feedback law that, so to say, compensates for nonlinearities. So as I said here, we would have, in the simultaneous method, we don't suffer from the nonlinearities because we just set the next linearization points to the points where the QP solver predicted them, so they are not getting accumulated. But if we do single shooting, we would, so to say, accumulate these things. So we would come somewhere. And this is not very good. And in ILQR, we have a chance to compensate for these things already, so we will, so to say, accumulate these errors, but we already reduce them a little bit. But I should also say this is a bit, you should treat it with caution, because if your system isn't controllable, for example, or for a moment not controllable at this linearization point or something, then it might actually be that you indeed still get very far away due to linearization errors, while the fully simultaneous method that just linearizes the trajectory where the QP solver thought it would be good, this method would, so to say, always linearize at the point where the QP solver said you want to be, which is more likely to be where you want to, where you will be at the very end anyway, right? So in that sense, the convergence properties, I think, are safer when you do fully simultaneous. That's one of the reasons why I prefer the fully simultaneous. And the second is that for the fully simultaneous method and for any other method, actually, it's easy to incorporate all the QP constraints, right? So this Riccati recursion is only for LQR. Once I have inequalities, I wouldn't have an easy way to represent this feedback law. I mean, MPC would be an option, but I don't want to apply MPC inside an MPC algorithm, so to say. And that would be overkill. I could solve QPs on a shrinking horizon or something, but this would be a crazy method because it's very expensive, and it's only for generating guesses for optimal solutions, right? So you rather say, and as I said before, my preferred method is the one where you just have a fully simultaneous state trajectory and you linearize at that, and then you do one QP after the other. But now that we are here in inventing mode, I want to, I'm just talking and not accepting questions, right? I want to still explain the ILQR real-time iteration that we didn't think of yet. But what would it be? It would just be that you take, basically think of what we would do, right? So we would say we have a current Riccati recursion. After we have finished our backward sweep, we have a new feedback law available. So then we take that feedback law to apply when we have the latest estimate. We directly apply that to the real system. And then we continue our forward pass with this nonlinear system and do a backward pass to get the new feedback law, and that's it. Yeah. So in that sense, it would also be a very elegant, nice algorithm. You do in every single iteration a forward and a backward pass, and you can also divide things into a feedback and preparation phase. So I think probably it exists already, but so we would have the ILQR RTI, so to say. How do you call it in the community?
No, I mean, actually, that's exactly what we did in this paper.
Okay, perfect.
The pendulum, the real
yes, yes, that's great.
We call it anything. We just said
but you called
it's ILQR, we do pre-computations.
Yeah.
And then once we get the new state, we apply the feedback law that we computed beforehand.
Who was the first author of that paper?
It's me.
Okay, that's perfect. Yeah. Bödecker. Which year? 2014. So in this pendulum swing up, this algorithm was used. Just one forward, one backward sweep. Perfect. Now we are really synchronized. Perfect.
So,
yeah.
Exactly. I mean,
yeah.
One forward, one backward.
Yeah.
I mean, you iterate to convergence in this preparations phase, then you have your feedback law, and once you get it,
okay, then it's slightly different. Okay. Or fully iterate. I mean, let me just, okay. There was this question, what would you do if you have lots of time in the preparation phase? And if you have lots of time in the preparation phase, what you could obviously do is iterate the problem which you think is the best problem that you know to convergence by doing several forward-backward sweeps. Or by, as we would say, several Newton iterations. You can do it with any method. So iterate to convergence at a state which you think is most likely to be the real state. And then prepare still, as we did before, the feedback. And then you measure the state and you directly apply to it. That's a slightly different method, and it's more related actually to what in the MPC community is called the advanced step MPC. It's also, I mean, Bigler and Zavala invented that, which, I mean, it's basically taking the IP-opt solver, solve the optimal control problem on the predicted state, and then computing sensitivities with similar methods like this one, but for the fixed active set. And then you have a feedback law that you could apply, so to say, immediately. Yeah? So in case of no active set, I think it would be the advanced step MPC. So we should make a connection between these papers. But that's really what ILQR, so to say, would boil down to. And I think it's an interesting mix between sequential and simultaneous. I still call it sequential because every trajectory is feasible, but it somehow is not this. Yeah, it's a mix because you actually get iterates that satisfy your system dynamics. I should say it's very difficult if you have state constraints. Like, for example, my preferred constraint, zero terminal constraint. Yeah? You will not really be able to hit it exactly with a nonlinear system simulation. The QP is able to hit it exactly. So if you have a zero terminal constraint, it will just directly set the first iterate to zero there. And yeah, and it will converge then quadratically to a trajectory that satisfies this constraint. But yeah, so once you have constraints like terminal constraints or bound path constraints, I think it's yeah. My point is I would use actually an SCP-based method because it's able to deal with these constraints. Maybe one way to save, let's say, the ILQR idea in this context would be to just do actually an interior point method around the ILQR loop. So you could say basically I work with barrier functions all the time, which makes my cost function very different, obviously. And then I modify this cost function while I do my Newton type iterations. So that would, so to say, be an IP-opt. You would just write an IP-opt with a structure exploiting algorithm. Which is could be an interesting option, yeah? But it's not exactly an IP-opt because you still have this nonlinear forward pass here. Mm-hmm. Thank you. I think that was good questions, but there was one more question, I think. The time is also nearly over. Yeah.
One question just regarding notation only. The first state trajectory we don't use at all, right? So the second one, so we recompute the state trajectory.
You mean here this notation? Okay, so I should say this this j plus 1 index here is different than this one. Yeah. So here we do not solve the QP. We never solve a QP, so to say. we get something that's approximately equal to it's not a QP solution because it uses, so to say, the QP thinking in order to generate the feedback law, but then it generates these trajectories, both S and A together, by the forward simulation of this closed loop system. So we basically,
this I plus 1j plus 1 is the same as the one above.
Yeah, this is so we obtain this by this. That's what I want. Yeah, we get this by that. So we get the new iterate by that, and this is the new iterate. That's the memory of our method. Actually, it's debatable what is really the memory of that method. Because you could also say that the real memory is, so to say, the controls. I mean, for a given control trajectory, you have obviously the corresponding state trajectory here. So you see there is no real memory in the S's. You could generate the S's by the A's. And after you have so if you have the A's, you can get the S. Then you can linearize. Then you can generate your new Riccati feedbacks, and then you can get your A's by this forward pass, but this forward pass accidentally also spits out already the S's, so to say. But the real memory, I think, is the A. So if you want to think of what is like iterated in this method. So you could initialize with a pure trajectory in the controls. And that's also how many people do it, I think. Yeah. Okay. Yeah.
Another question regarding how would the procedure look like with inequality constraints in order to do the Riccati backwards?
Yes, so exactly. So the very good question. So the question is, how would all these procedures deal with inequality constraints? And I obviously didn't explain that at all. Maybe the first answer is the ILQR, like it is explained here, is not able to be applicable. Yeah? For the SVP, you have an easy way around, because you could just say, if I have a convex problem, I can solve a convex problem. Yeah? And okay, that's of course now delegating all the difficulty to the QP solver. Yeah? But actually what we do, yeah, is we say we have a good, or we know how to solve QPs. And so then you take this quadratic problem and you just solve it, and then you get from this new trajectories like these. Where do we have them? This x, j plus 1 is actually obtained from the QP solver. But inside the QP solver, for example, if you go inside HPIPM, which would be one of the QP solvers that is really tailored to this type of problem, it would do Riccati sweeps all the time, right? It would just do probably like 10 forward-backward sweeps of your Riccati iteration for different barrier parameters. And after about 10, maybe 20 QP forward-backward sweeps, it has solved the QP exactly. And if you want to survive with a very inaccurate solution, you could maybe even do only 2 or 3 sweeps. But please note that inside an interior point method, you have this barrier parameter, which basically makes your problem different. So if you have you make it much easier by a big barrier parameter, and then you make it more accurate, but also more difficult to solve for a high barrier parameter. So you need the homotopy to start with a big parameter, make it smaller, in order to be able to treat this very strong nonlinearity due to the inequalities correctly, right? Because, I mean, you get, with active set methods, you do it very differently, but with this method, you just keep in the interior of your problem. You start very much in the interior, and then you relax it, so to say, until you come to the boundaries. But this is then done with forward-backward sweeps again. So at the bottom, you would have forward-backward sweeps. What is another synergy that now comes to my mind? Why is HPRPM fast? It is fast because it does all the Riccati iteration with Blasfeo. So we could look at what it, I mean, typically there's a factor of 10, as I said, depending on what CPU you have. So we could just look at how to do it with Blasfeo. No? That would be another simple modification. ILQR with Blasfeo as a idea. I think maybe people at ETH did something like that already. I forgot, but there's a nice software package out there. Okay, good. We have now elucidated a bit the connections between Joschka's point of view and my point of view to, let's say, deterministic differentiable system optimization. Yeah? Thank you very much. Yeah, more questions.
Yeah, another question. And why is this ILQR approach so famous in reinforcement learning, in the reinforcement learning area?
So the question is, why is ILQR so famous in the reinforcement learning area? Maybe I start my point of view, and then Joschka continues. So maybe one really interesting historical remark is there is an algorithm that's called differential dynamic programming, DDP. And that is, I think, from 1966. Yeah, it's really as old as this, right? Incredibly old. And that's basically this algorithm with a second order, it's so to say the more advanced variant, more difficult to explain, where you would take an exact Hessian. But the main point is that you get also this feedback propagation in a nonlinear way there. So this algorithm is by Main and others at that time. And because it was, it's a nice and successful method, which was, it's structure exploiting. Before sparse linear algebra was available, you would have it, so to say, for free. It's very intuitive and nice. And Yeah, and it's better than single shooting, which was used a lot at that time. So in that sense, DDP is already, I think, a better algorithm than standard single shooting, and it's when you're happy without constraints, it's a really useful algorithm. And I think when you combine MPC with inequality constraints, it's typically not useful anymore. So that's my main reason, so to say, to switch to, SCP type methods or interior point methods in general is that I want to deal with the inequalities. That would be the reason not to use them. But I think if you are, so to say, not having inequalities, it's a good algorithm. And historically, that's now my point of view, and maybe you can say it, I think